Welcome back. Today we are covering celestial navigation, sextant angle corrections. So to summarize where we are at so far in regards to our celestial navigation studies, we have covered the sextant and how to take a reading, the measurement of time in the celestial sphere. Today we are going to have a look at the measurement figure we got from the sextant and the corrections that need to be made to that figure before we can start working out our position. A sight reduction form comes in very handy when it comes to working out your sights. The whole form is a bit scary to look at all at once, so I'm going to break it down into manageable bites. Here is the first part, and covers just the corrections we are going to talk about today. You can see that in 1, you write in the celestial body you are measuring. So in our case, we are going to use the sun. Then write the angle you took with your sextant, HS, in the 4th box down, sextant altitude. The adjustments should be made in the following order. Instrument correction. When sextants are being made, there could be some imprecise machining of the arc, which can cause a permanent error in what the sextant tool reads. These corrections are established by the manufacturer and are noted in the certificate of accuracy, which can usually be found inside the lid of the sextant box. Mine doesn't have one. You can disregard any corrections smaller than 0.3 of arc. Your sextant could possibly be certified as having no significant error, in which case you don't even need to worry about this correction at all. There isn't a specific box for instrument correction in the table above, but you can combine it with your index correction. Remember when we were checking the sextant for any errors back in the first post? If you were unable to remove the errors by adjusting the screws on the back of the sextant mirrors, then you can instead use a mathematical calculation using the number you noted down as being your index correction. If the error is on the arc, if it is greater than 0 degrees, then you need to subtract the error. If it is off the arc, if it is on one of the blank lines to the right of the 0 degrees in the picture above, then you add the error. You can remember it by saying, if it is on, take it off, and if it is off, then add it on. Put this figure in the index correction box on the table above. Dip, D, or dip, height of eye correction. If you are taking your sextant readings from the bridge of a big ship, then you're going to get a different sextant reading to if you were on a small yacht. Therefore, we need to make a correction to what your sextant says to get your reading converted to a sea level reading. This is called dip, or an adjustment for your height of eye. Take a look at the table here. On the right-hand side is a column called dip. Imagine that if you are standing up on the side of a small yacht when taking your sextant reading, you are likely to be about 3 meters above sea level. If you look down the table until you get to 3.1 and then look across to the number beside it, you will see 3.1. This is our dip figure, and it is always subtracted from the sextant reading. Put the dip correction into the table above and combine with the index correction and sextant altitude to get He, or total apparent altitude. You might note that the table below only covers angles from between 10-90 degrees. There is another table for between 0-10 degrees, but it is preferable to have an angle of greater than 10-0 to get a better level of accuracy. Total, third or combined correction. If the number you get is exactly the same as the value on the table, then use the correction figure on the line above. Do you remember in the first video when we talked about getting the bottom of the sun just touching the horizon in our sextant mirror? This is called the lower limb of the sun. You can also take a measurement of the top limb of the sun. For example, if the bottom of it was covered in cloud or a star. What we really want to know is the angle between the horizon and the middle of the sun. But of course, that is pretty hard to estimate. So we have to do a bit more maths to figure out the distance between either the top or bottom limb of the sun and its center. The other correction included in this figure is refraction, or distortion of the angle of the sun as it comes through the atmosphere. It is all conveniently worked out for you in the tables. So in the left-hand column on the table above which says sun, you will note that there are 2 columns depending on the month of the year. So say we are in October and we measure the lower limb of the sun at an angle of 18 degrees. If you look down the column until you get to 18 degrees, you can see that the correction is Doan 13.3. If we were measuring the upper limb of the sun in October, then we would make a correction of 19.0. Make a copy of the table above and put it in your navigation folder. You can use this for all your equations as you move on. Quiz okay, let's check what we have learned here. And please feel free to comment if you think I have made any mistakes. The month is July. You have an index correction of 2.3 on the arc. Your height of eye is 5 You measure the lower limb of the sun at 20 degrees 30. 5 I've typed it out as if I was completing the boxes above. Use the table provided here to work out the dip and altitude correction. I get sun lower limb IC went 2.3. If it's on, then take it off. Dip what 4.0. We always subtract dip HS white 20 degrees 35, just with what we read on the sextant. How white 20 degrees 24.222. All the above combined together. Altitude correction when we are 13.4, as per the table relating to our hay figure. No other corrections for atmosphere or planets Hawaii 20 degrees 37.26, plus the altitude correction. No other corrections for atmosphere or planets. Do you agree? 2. The month is October. We have an index correction of 3 potes off the arc. Your height of eye is 10. We are on a flash launch. You measure the upper limb of the sun at 17 degrees 15.8. Sun upper limb. I get sun upper limb IC to 3L. If it is off, add it on. Dip watch 5.6. We always subtract dip HS 17.015.8 as per what we read on the sextant. Hopwa 17.013.2 HS dip IC altitude correction Watt 19.1 as per the table using the HA figure. No other corrections for atmosphere or planets Hawaii 16.054.1. Remember, there are only 60s in each degree, so hopefully I have worked that out correctly. If you are better at math than I am, please comment to let me know. 3. The month is August. We have an index correction of 2.1 on the arc. Your height of eye is 4.5. You measure the lower limb of the sun at 43 degrees 55. I get sun lower limb IC wench 2.1. If it's on, then take it off. Dip watt 3.8. We always subtract dip H is Wayne 43 degrees 50.5 as per the reading from the sextant. Haori's 43 degrees 44.6, combining all the figures above. Altitude correction and Shaber 15.0 as per the table using the hay figure above. No other corrections for atmosphere or planets Hawaii 43 degrees 59.6. 4. The month is November. We have an index correction of 2.7 off the arc. Your height of eye is 2.9 mm. You measure the lower limb of the sun at 24.019 pre. I get sun lower limb IC 1.27. If it's off, add it on. Dip what 3. Found on the table. We always subtract dip HS what 21 degrees 19.3. As per the reading from the sextant, how wash 21 degrees 19 pula, combining all the figures above. Altitude correction 13.8. No other corrections for atmosphere or planets. Hawaii 21 degrees 32.8. If you fancy making up any more examples to work out in the comments below, please do. I could do with all the practice I can get.